Tonight, we're going to shrink down to a scale so small that your mind is not built to hold it. A single atom. Something you cannot see, cannot touch, cannot photograph with any camera that has ever existed. And yet everything around you, this screen, your hands, the air filling your lungs right now, is made entirely of these things. Billions upon billions of them, packed together so tightly that they feel solid. But here's what's going to unsettle you. The atom isn't mostly solid. It isn't mostly anything. It is almost entirely empty space. If you could see one clearly, you would find a tiny speck of matter surrounded by a vast, mostly hollow volume, held together by forces so strange that physicists spent centuries just trying to describe what was actually happening inside it. By the end of tonight, you're going to understand exactly how small an atom really is, why almost all of it is nothing at all, and why that emptiness is the reason you can stand on solid ground without falling straight through it. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something familiar. A single grain of ordinary table salt. The kind sitting in a shaker on any kitchen table anywhere in the world. That grain is a crystal of sodium and chloride atoms bound together in a repeating lattice, and it measures roughly 300 micrometers across. 300 micrometers is about 3/10 of a millimeter. You can barely see it without squinting. Set it on a white piece of paper, and it appears as a tiny, nearly transparent speck that most people would brush away without a second thought. Now hold that grain of salt in your mind, because we are going to use it as our starting point, and we're going to go smaller and smaller and smaller still, until we've reached something that makes that grain of salt look like the entire observable universe by comparison. That's not poetic exaggeration. When we get to the proton sitting at the center of a hydrogen atom, the ratio of sizes between that grain of salt and the proton is roughly 10 billion to 1. About the same ratio as between the observable universe and the solar system. Let's begin at the atomic level. The sodium atom has a radius of roughly 186 picometers. A picometer is 1/1,000,000,000 of a meter. 11 zeros after the decimal point before you reach the 1. This unit has essentially no meaning in everyday life because nothing in everyday life operates at this scale. There is no everyday analogy that captures it cleanly. But here is one attempt. 1 millimeter, roughly the width of a thin guitar string, contains about 4 million sodium atoms laid side by side. 4 million. A single human hair, somewhere between about 70 and 100 micrometers wide, contains roughly 300,000 to 500,000 atoms stacked across its diameter. And that's the atom's full width, nucleus and surrounding electron cloud included. When we get inside the atom, the numbers will become stranger still. To understand the true scale of an atom, you have to understand why measuring it requires a fundamentally different approach than measuring anything else. The tools of everyday life stop working long before we get anywhere near atomic scale. The best optical microscope in the world, using visible light, cannot see individual atoms. Visible light has wavelengths between roughly 400 and 700 nanometers. A nanometer is 1/1,000,000,000 of a meter, and individual atoms are typically between 1/10 and half a nanometer in diameter. The atom is smaller than the wavelength of the light we would use to look at it. When the wavelength of light is larger than the object you're trying to see, the light simply bends around the object and carries no information about it. This is not a limitation of lens quality or sensor resolution. It's a hard constraint built into the wave nature of light itself. You cannot use visible light to see an atom, ever, regardless of how good your microscope is. To see atoms directly, physicists had to invent entirely new instruments. Electron microscopes, which use beams of electrons rather than photons of light, can resolve structures down to about 50 picometers. Electrons have much shorter wavelengths than visible light, which is why they can reveal finer detail. But even electron microscopes have limits when it comes to imaging individual atoms in their natural environments. The real breakthrough came with scanning probe microscopy. The scanning tunneling microscope, invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM's Zurich Research Laboratory, doesn't form images the way a camera does. It drags an incredibly sharp metallic tip across a surface at a distance of just about 1 nanometer, so close that electrons from the surface can tunnel quantum mechanically through the gap to the tip. This tunneling current is extraordinarily sensitive to distance. Move the tip even slightly closer or farther from the surface, and the current changes dramatically. By keeping the current constant as the tip moves across the surface, or by measuring how much the tip height must change to maintain constant current, you can map the positions of individual atoms on the surface with subatomic precision. Binnig and Rohrer received the Nobel Prize in Physics in 1986 for their invention, 4 years after they built the first working model. And what these instruments revealed when we finally had eyes sharp enough to see individual atoms was genuinely surprising. Atoms look nothing like the textbook diagrams most of us grew up with. The history of how humanity figured out what atoms actually are is not a detour. It's essential context for understanding why the scale of an atom is so startling. It took roughly 2,500 years from the first philosophical speculation that matter might be made of indivisible units to the first confirmed image of a single atom. The ancient Greek philosopher Democritus proposed the idea around 400 before the Common Era. He called the smallest possible piece of matter atomos, meaning uncuttable or indivisible. For most of that 2,500-year span, the atom was purely philosophical, a thought experiment, an elegant idea with no physical evidence behind it. The first real scientific case for atoms came from chemistry in the early 1800s. The English chemist John Dalton noticed something striking about the way chemical substances combine. When hydrogen and oxygen combine to form water, they always combine in the same fixed ratio by mass. 8 grams of oxygen for every 1 gram of hydrogen. Exactly. Without exception. This wasn't an approximation or a tendency. It was a law. And Dalton recognized that the most elegant explanation was that matter comes in discrete units with fixed masses. If hydrogen atoms have a certain mass and oxygen atoms have a different mass, and every water molecule contains exactly 2 hydrogen atoms and 1 oxygen atom, then the mass ratio is determined by structure, locked in. Dalton didn't know what atoms looked like. He didn't know their sizes. But he established that they had to exist. By the mid-1800s, chemists had identified dozens of elements, each with its own atomic mass, each combining with others in fixed whole number ratios. The periodic table, first organized systematically by Dmitri Mendeleev in 1869, revealed patterns in those masses that suggested atoms themselves had internal structure. Something was going on inside the atom. The atom was not the end, and it took another generation of experiments to find the first door inside. That door opened in 1897. J. Thomson, working at the Cavendish Laboratory in Cambridge, was studying cathode rays The glowing beams produced in evacuated glass tubes when a high voltage is applied between metal electrodes. These rays had been observed since the 1860s. Debate continued over whether they were waves or particles. Thomson settled it. He showed that cathode rays could be deflected by electric and magnetic fields, which meant they carried electric charge. They were particles. He measured the deflection carefully and calculated the ratio of charge to mass for the particles making up the ray. The ratio was roughly 1,800 times larger than that of the hydrogen ion, the lightest charged particle known at the time. Either these particles carried an enormous charge, or they had an extremely tiny mass. Thomson showed the charge was normal. The mass was tiny. These particles were far smaller and lighter than any atom. He had discovered the first subatomic particle, the electron. This was a genuine shock. If atoms contained electrons, atoms were not the indivisible units Dalton had imagined. They had internal structure. Something was inside. Thomson proposed a model. He imagined the atom as a uniform sphere of diffuse positive charge with electrons embedded inside, like raisins distributed through a pudding. This became the plum pudding model. It was wrong. But the wrong model made specific, testable predictions. And testing those predictions led to the most consequential experiment in the history of atomic physics. Ernest Rutherford, working at the University of Manchester with Hans Geiger and Ernest Marsden, performed that experiment in 1909. They directed a beam of alpha particles, which are helium nuclei, at a piece of gold foil just a few hundred atoms thick. If Thomson's model was correct, the diffuse positive charge inside each atom would deflect the incoming alpha particles only gently. The beam should pass through mostly straight, scattering only slightly. That was the expectation. That was not what happened. Most alpha particles did pass straight through, but some were deflected at surprisingly large angles, and a very small number bounced almost straight back the way they came. Rutherford later described this result as if you fired artillery shells at tissue paper and they came back and hit you. The backward scattering made absolutely no sense under Thomson's model. A diffuse positive charge cannot deflect a fast-moving particle backward. For a particle to bounce backward, it has to strike something very small, very dense, and carrying a large amount of concentrated charge. Rutherford spent about 2 years analyzing the results. And the picture that emerged was not gradual or incremental. It was a complete restructuring of how atoms had to be imagined. The positive charge of the atom, and almost all of its mass, was not spread through the atom's volume. It was concentrated in an almost impossibly small central region, the nucleus. The electrons were orbiting far outside, at distances vast compared to the nucleus, and in between, nothing. Essentially, nothing. When Rutherford worked out the numbers, the picture became staggering. If a hydrogen atom was scaled up to the size of a large sports stadium, the nucleus, the proton, would be about the size of a pea sitting at the center of the field. The electron would be somewhere in the stands, and the entire volume in between would be empty. Your hand is almost entirely empty space. Your entire body is almost entirely empty space. Every physical object you have ever touched in your entire life is almost entirely empty space. The sensation of hardness and solidity that you experience when you touch something is not matter meeting matter. It is electromagnetic repulsion between the electron clouds of atoms. When you set your hand on a table, what prevents your hand from passing through is not solid material. It's the fact that the electron clouds of the atoms in your hand and the atoms in the table repel each other. Their negative charges push back against each other. You've never actually made direct contact with anything in the nuclear sense. Not once. Not ever. Now, let's assign real numbers to this emptiness. A hydrogen atom, the simplest atom, consisting of one proton and one electron, has a radius of about 53 picometers. This is called the Bohr radius, named after Niels Bohr, who derived it from quantum mechanics in 1913. 53 picometers is about 5.3 times 10 to the power of negative 11 meters. The proton at the center of that atom has a radius of about 0.85 femtometers. A femtometer is 1/4,000,000th of a meter, 1,000 times smaller than a picometer. So the proton's radius is roughly 0.85 times 10 to the power of negative 15 meters. Now, let's think about the ratio. The atom's radius is about 53 picometers, which is 53,000 femtometers. The proton's radius is about 0.85 femtometers. The atom is therefore about 62,000 times wider than its own proton. In 3 dimensions, the volume of the atom is about 62,000 cubed larger than the volume of the proton. That's roughly 240 trillion times larger. 240 trillion. That is the amount by which the atom's volume exceeds the volume of its own nucleus. All of that excess volume is occupied by the electron's probability cloud, which is not the same as solid matter, not even slightly. Here's a way to feel that ratio, rather than just read it. Imagine the proton scaled up to the size of a marble, a standard glass marble, about 15 millimeters in diameter. If the proton is that marble, then the electron's average orbital radius would be at a distance of roughly 900 meters, nearly a kilometer away. You would have to walk almost a kilometer from the marble to reach the boundary of the atom. In the entire space between the marble and that boundary, there is no solid material, no orbiting electron following a fixed circular track like a tiny moon. Just the quantum mechanical probability cloud of the electron, a spread-out description of where the electron is likely to be found if you were to look for it. And this brings us to the point where classical intuition stops being useful entirely. We want to imagine the atom as a tiny solar system, a miniature sun at the center, with electrons zipping around in circles. That picture is wrong. It was wrong when Rutherford proposed it in 1911. Bohr modified it in 1913, and it was still wrong, or at least incomplete in the same fundamental way. Electrons do not orbit in fixed paths the way planets orbit the sun. They exist in quantum states, probability distributions, orbitals. An orbital is not an orbit. An orbital is a region of space where the electron has a certain probability of being found. The simplest orbital, the one relevant for a hydrogen atom in its lowest energy state, is spherically symmetric. The electron has roughly 90% probability of being found within a certain radius of the nucleus, and the probability falls off beyond that. But there is no defined edge. There is no wall. The electron could theoretically be found quite far from the nucleus, though with rapidly decreasing probability. And in quantum mechanics, we don't just mean we don't know where the electron is. We mean the electron genuinely doesn't have a definite position. Not until something interacts with it and forces it to have one. Position is not a property the electron carries around with it between measurements. This is not a philosophical interpretation layered on top of the physics. It's what the mathematics says. And the mathematics has been tested against experiments to a precision that no other theory in science has matched. Here is a question that sounds simple. Why doesn't the electron spiral into the nucleus? The electron carries negative charge. The proton carries positive charge. Opposite charges attract. Electromagnetism is pulling the electron toward the proton continuously. So what holds the electron at a distance? In classical physics, there is no satisfying answer. A charged particle moving in a curved path accelerates, and an accelerating charged particle emits electromagnetic radiation. When it emits radiation, it loses energy. As it loses energy, it spirals inward. A classical hydrogen atom would collapse entirely in about 10 to the power of negative 11 seconds, essentially instantly. The atom should not be stable. Matter should not be stable. We should not exist. And this was not a theoretical puzzle. It was a genuine crisis in physics at the turn of the 20th century. Quantum mechanics was born, in large part, to resolve it. In quantum mechanics, electrons can only occupy certain discrete energy states. The lowest state, the ground state, is as close as the electron can get to the nucleus. Not because of any physical barrier, but because of a fundamental relationship between confinement and energy. To confine the electron more tightly, to squash its probability distribution into a smaller region, requires giving it more momentum, uncertainty. More momentum uncertainty means higher average kinetic energy. At some point, the energy cost of further confinement outweighs the energy gain from getting closer to the nucleus. The atom finds an equilibrium, a size at which the total energy, kinetic plus potential, is minimized. That size is the Bohr radius. The atom is the size it is because quantum mechanics sets a floor. And the Heisenberg uncertainty principle, which states that the position and momentum of a particle cannot both be simultaneously known to arbitrary precision, is what creates that floor. This principle is not about the clumsiness of measurements. It's not about how instruments disturb things when they measure. It's a statement about reality itself. At the quantum scale, position and momentum are genuinely complementary properties. More certainty in one means less in the other. Not because of ignorance, because that's how nature works. And the atom, with all its emptiness and all its strangeness, is stable because of this. We are here because of this. Let's think about what the electron actually is. Because it's one of the most important things in the universe, and its nature is stranger than most descriptions give it credit for. The electron is, as far as physicists can determine, a fundamental particle. Unlike the proton, which has internal structure we'll get to in a moment, the electron shows no signs of being made of anything smaller. It appears to be a point particle, meaning it has no measurable physical size. Its charge is distributed over no volume. It's not a tiny sphere. It's a mathematical point, with charge and mass and spin. In quantum field theory, which is the most fundamental description we have, the electron is an excitation of the electron field. The electron field is a quantum field that permeates all of space. It exists everywhere, at every point in the universe, simultaneously. Most of the time, this field is in its ground state, which means it has no particles in it. But when enough energy is added to a region, the field can be excited, and that excitation manifests as an electron. Or a positron, the electron's antiparticle, depending on the details. The electron is not a tiny object sitting inside the atom. It's a localized, quantized disturbance in a field that fills the universe. This is true of all fundamental particles. Quarks are excitations of quark fields. Photons, the particles of light, are excitations of the electromagnetic field. The Higgs boson, detected at CERN in 2012, is an excitation of the Higgs field. The universe, at its most fundamental level, is not made of objects sitting in space. It is made of fields that fill all of space, vibrating, fluctuating, interacting with each other, and those interactions are what we perceive as particles, forces, and matter. This picture, quantum field theory, is the framework underlying the standard model of particle physics. And it is the most precisely tested physical theory in history. Quantum electrodynamics, the quantum field theory of electromagnetism, predicts the magnetic moment of the electron, a measure of how strongly it responds to magnetic fields, to roughly 1 part in a billion. The agreement between prediction and measurement is better than the agreement between any other theoretical prediction and any other experimental measurement in all of science. The electron field is real. Quantum fields are real. The picture of particles as localized excitations in those fields is as well established as anything in physics. Now let's go inside the nucleus. Rutherford discovered that the nucleus exists, that it's tiny and dense and carries the atom's positive charge. But the nucleus was not the end of the story. Rutherford himself suspected there was more structure inside. He proposed in 1920 that the nucleus might contain a neutral particle alongside the protons, something he called a neutron. He was right, but the experimental confirmation came 11 years later. In 1932, James Chadwick, working at the Cavendish Laboratory in Cambridge under Rutherford, showed that when beryllium was bombarded with alpha particles, it emitted a radiation that could knock protons out of materials containing hydrogen. This radiation had to consist of particles with no electric charge, but with a mass similar to the proton. Chadwick had confirmed the neutron. The nucleus is made of protons and neutrons, which physicists collectively call nucleons. The number of protons in a nucleus determines which element it is. Hydrogen has 1 proton. Helium has 2. Carbon has 6. Iron has 26. Gold has 79. Uranium has 92. Neutrons add mass without changing the element's identity. Atoms of the same element, with different numbers of neutrons, are called isotopes. Carbon 1,2 has 6 protons and 6 neutrons. Carbon 1,4 has 6 protons and 8 neutrons. Carbon 1,4 is radioactive, meaning the nucleus is unstable and will eventually transform by emitting a particle. This radioactive decay is what makes carbon dating of ancient materials possible. Living things constantly exchange carbon with the environment, maintaining a certain ratio of carbon, 1,4 to carbon, 1,2. When something stops living, the exchange stops, and the carbon, 1,4, begins to decay at a known rate. By measuring how much carbon, 1,4 remains relative to carbon, 1,2, you can calculate when the exchange stopped. That's the age of the material. The whole technique rests on the nuclear physics of the carbon atom, on the structure of a nucleus that is less than a femtometer across. For several decades after Chadwick's discovery, the picture of the atom was protons and neutrons in the nucleus, electrons orbiting outside. Simple, satisfying, but wrong again, or rather, incomplete. In the 1960s and 70s, physicists firing beams of high-energy electrons at protons began noticing something unexpected. The electrons didn't scatter the way they would if the proton were a smooth, uniform sphere of charge. They scattered in patterns that suggested there were smaller, point-like objects inside the proton. Hard scattering centers that the electrons were bouncing off. The theoretical framework explaining this was developed by James Bjorken and Richard Feynman, among others. Bjorken showed, through scaling arguments, that the proton had to have internal structure. Feynman called the hypothetical internal components partons. They turned out to be quarks. The quark model had been proposed independently by Murray Gell-Mann and George Zweig in 1964. Gell-Mann, who borrowed the word from James Joyce's Finnegan's Wake because he liked the sound of it, proposed that protons and neutrons were made of 3 quarks each. There are 6 types of quarks. Physicists call them up, down, strange, charm, bottom, and top. The proton contains 2 up quarks and 1 down quark. The neutron contains 1 up quark and 2 down quarks. Up quarks carry an electric charge of positive 2/3. Down quarks carry a charge of negative 1/3. 2 up quarks and 1 down quark. 2/3 plus 2/3 minus 1/3 equals 1. The proton's charge of positive 1. 1 up quark and 2 down quarks. 2/3 minus 1/3 equals 0. The neutron's charge of exactly 0. The arithmetic works out cleanly, which is one of the reasons physicists found the quark model compelling before the direct experimental evidence was overwhelming. Quarks are bound together inside protons and neutrons by the strong nuclear force. And the strong nuclear force behaves in a way that has no analog in everyday physics. Every force we experience in daily life, gravity, electromagnetism, the friction of surfaces, weakens with distance. Move 2 magnets farther apart, and the force between them decreases. The strong force doesn't work this way. At the distances inside a proton, the strong force is relatively weak. The quarks move around semi-freely. But try to pull 2 quarks apart, and the force doesn't decrease as the distance grows. It stays roughly constant, like a rubber band that never loses its tension. If you put enough energy into trying to separate 2 quarks, at some point you've pumped in enough energy that the field between them spontaneously creates a new quark-antiquark pair from the vacuum. The new quark attaches to one end. The new antiquark attaches to the other. You end up with 2 hadrons instead of 1 isolated quark. This property is called confinement. Single, isolated quarks don't exist in nature. They've never been observed. They almost certainly cannot be observed because the act of trying to isolate one creates new particles. Quarks are permanently confined inside the particles they make up. This is not a practical limitation. It's a fundamental feature of how the strong force works. And it means that the quarks inside the proton in the center of every atom in your body are, in a meaningful sense, trapped forever. They have been since they were created in the first moments after the Big Bang. They will remain trapped until the proton itself decays, if it ever does. And the proton may be essentially stable, with a lifetime longer than the current age of the universe by many orders of magnitude. Those quarks are not going anywhere. The mass of quarks adds another layer of strangeness. Up quarks have a mass of roughly 2.2 megaelectronvolts divided by c squared. Down quarks have a mass of roughly 4.7 megaelectronvolts divided by c squared. The combined mass of the 3 quarks in a proton is about 9 mega-electron-volts divided by c squared. But the proton's measured mass is 938 mega-electron-volts divided by c squared. The quarks account for less than 1% of the proton's mass. Where does the other 99% come from? From energy. From the intense, seething energy of the gluon field inside the proton. Gluons are the particles that carry the strong force between quarks. They're massless particles, like photons. But the field they create, the constant exchange of gluons between quarks, stores enormous energy. And E equals mc squared. Energy is mass. The mass of the proton is almost entirely the binding energy of the strong force. The mass of ordinary matter, the mass of your body, the mass of everything you've ever touched, and every mountain and every star, is almost entirely energy stored in force fields inside atomic nuclei. Not the mass of quarks themselves. Energy. When Einstein wrote E equals mc squared, people imagined it as a formula for releasing energy from matter, for nuclear bombs and reactors. And it is that. But it's also the explanation for why matter has mass in the first place. The proton has mass because of energy locked inside it. The gluon field is converting energy to mass every moment, in every proton, in every atom, everywhere in the universe. There is another layer of quantum strangeness inside the nucleus. The strong force is carried by gluons, but it doesn't just act between quarks. It also acts between protons and neutrons, holding the nucleus together against the electromagnetic repulsion between the positively charged protons. Protons have the same electric charge, and like charges, repel. In a nucleus with 2 protons, the repulsion is manageable. In a nucleus with 26 protons, like iron, it's significant. In a nucleus with 92 protons, like uranium, the balance is delicate. The residual strong force, sometimes called the nuclear force, acts over distances of about a femtometer or 2. Within that range, it's powerful enough to overwhelm the electromagnetic repulsion. Beyond that range, it falls off rapidly. This is why there's a limit to how large a stable nucleus can be. As you add more protons, the electromagnetic repulsion grows. The nuclear force, acting only at very short range, can't compensate indefinitely. At some point, beyond a certain number of protons, no stable nucleus exists. The largest naturally occurring element is uranium, with 92 protons. Elements beyond uranium exist only briefly, created in particle accelerators or in the extreme conditions of stellar explosions, before decaying. The size of naturally occurring atoms is limited by the physics of what happens inside a space smaller than a femtometer, by the competition between the strong force and electromagnetism at the smallest scales we can probe. The electron's charge is exactly equal in magnitude to the proton's charge, but opposite in sign. One carries +1. The other carries -1. Exactly 1. Not approximately. Not almost. Exactly. To a precision that experiments can measure, which is better than 1 part in 10 to the power of 21. This equality is remarkable. The proton and the electron are completely different particles. The proton has a mass 1,836 times larger than the electron. The proton has internal structure. The electron appears to be a true point particle. They interact through completely different forces. And yet, Their charges are equal to a precision that no theory has fully explained. If the charges were not exactly equal, matter as we know it could not exist. Atoms would not be electrically neutral. The universe would be saturated with electromagnetic fields that would prevent the formation of any complex structure. There would be no stars, no planets, no chemistry, no biology. No anything that requires neutral atoms. The equality of proton and electron charge is one of the deep, unexplained facts about the universe. It may follow from some symmetry we haven't fully understood yet. It may be explained by the eventual discovery of a relationship between quarks and electrons that isn't apparent in the standard model. Or it may be one of those things that physics will eventually trace to something deeper still. For now, it's a fact we rely on, but can't fully explain. Hydrogen deserves specific attention. It's not just the simplest atom. It's by far the most abundant atom in the universe. About 75% of all ordinary matter by mass is hydrogen. Most of the rest is helium, created in the first few minutes after the Big Bang during a process called Big Bang nucleosynthesis. All the heavier elements, everything from lithium through uranium, make up only about 2% of ordinary matter by mass. We live on a planet made of heavy elements, which can make us feel like heavy elements are common. They're not. The universe is overwhelmingly hydrogen. Every star in the sky is mostly hydrogen. The vast clouds of gas between galaxies are mostly hydrogen. The hydrogen atom consists of a single proton and a single electron. Nothing else. No neutrons in the most common isotope. Just one proton, one electron, one atom. And the study of hydrogen is central to quantum mechanics in a way nothing else matches. Because hydrogen is simple enough to solve exactly. Exactly means precisely, not approximately. Schrödinger's equation, the fundamental equation of quantum mechanics that describes how particles evolve over time, can be solved analytically for the hydrogen atom. You can write down, in closed form, the exact wave functions for every energy state of the electron in hydrogen. And the predictions those wave functions make match the observed behavior of hydrogen to extraordinary precision. The hydrogen spectrum, the specific wavelengths of light that hydrogen absorbs and emits, was known experimentally long before quantum mechanics was developed. Johann Balmer, a Swiss mathematics teacher, discovered in 1885 that the wavelengths of visible light emitted by hydrogen followed a simple mathematical formula. The Balmer series, as it became known, produces lines at about 656 nanometers, a deep red, 486 nanometers, a blue-green, 434 nanometers, violet, and 410 nanometers, deep violet. These four lines are the fingerprint of hydrogen, and they appear in the spectra of stars across the universe, allowing astronomers to identify hydrogen everywhere they look. Quantum mechanics explained why those specific wavelengths, and no others, appear. Each line corresponds to the electron falling from one quantum energy state to another. The red line corresponds to the electron falling from the third energy level to the second. The blue-green line corresponds to the fall from the fourth level to the second. The energy of each photon emitted equals the energy difference between the two levels, which determines its wavelength. The energy levels of hydrogen can be calculated from Schrödinger's equation. They were also calculated from simpler models first. Niels Bohr, in 1913, derived the energy levels from a semi-classical model. getting the right answers for the wrong reasons. Full quantum mechanics arrived in 1925 and 1926 from Werner Heisenberg and Erwin Schrödinger independently, and it explained not just which wavelengths appear, but why the hydrogen spectrum looks the way it does, with the mathematical rigor that Bohr's model lacked. The hydrogen spectrum isn't just a curiosity. It's a tool that has unlocked the universe. Because light carries a spectrum, and spectra are fingerprints, astronomers can identify the chemical composition of objects they will never visit, of stars thousands of light years away, of galaxies billions of light years away, of the gas between galaxies. Every absorption line, every emission line, corresponds to a specific atomic transition, to a specific quantum mechanical process inside a specific type of atom. When you look at the spectrum of a distant star and see the hydrogen lines shifted slightly toward longer wavelengths, toward the red end of the spectrum, you know the star is moving away from you. The Doppler effect stretches the light to longer wavelengths, the same way a receding ambulance siren drops in pitch. This is how Edwin Hubble, in 1929, discovered that distant galaxies were receding, that the universe was expanding, that the Big Bang had happened. All from the behavior of atomic transitions, from the quantum mechanics of the hydrogen atom. The universe was revealed to be expanding because atoms have fingerprints, and those fingerprints shift in a way that reveals motion. The atom is not just a piece of matter. It's a measuring instrument built into the fabric of everything. Let's think about what holds atoms together when they combine to form molecules. Because atoms don't usually exist in isolation. They bind to each other through chemical bonds, forming the molecules that make up everything from water to DNA to the proteins in your cells. Chemical bonding is, at its root, electromagnetic. It happens because electrons from one atom can interact with the nucleus of a neighboring atom. When two hydrogen atoms approach each other, the electron from one can spread its probability distribution to include the nucleus of the other. The result is a lower energy state than the two atoms had separately. The system stabilizes by forming a covalent bond where the two electrons are shared between both nuclei. This sharing, this spreading of electron wave functions across two nuclei simultaneously, is what holds the molecule together. And the energy released when atoms form bonds is the energy that drives chemistry. Every chemical reaction in your body, every metabolic process, every signal transmitted between neurons, every muscle contraction, every moment of perception, is driven by electrons rearranging their positions around atomic nuclei, by quantum mechanical probability waves shifting from one configuration to a lower energy one. Life is quantum mechanical at its foundation, not in a metaphorical or mystical sense. In the literal sense that the chemical processes underlying biology obey quantum mechanics. Enzyme catalysis involves quantum tunneling, the ability of particles to pass through energy barriers they classically shouldn't be able to cross. Photosynthesis involves quantum coherence, where excitations spread quantum mechanically across molecular complexes to find the most efficient path to a reaction center. The structure of DNA, the double helix, depends on specific hydrogen bonds between base pairs that are determined by the quantum mechanical properties of their atoms. These processes aren't classical. They depend on specifically quantum effects. Without quantum mechanics, life as we know it would not function. Without quantum mechanics, atoms would not be stable. The universe would not have the structure needed for anything to exist. Let's zoom out from the individual atom and think about what you're actually made of. A human body contains roughly 7 times 10 to the power of 27 atoms. 7 octillion. Written as a number, that's a 7 followed by 27 zeros. The composition is approximately 65% oxygen by mass, 18% carbon, 10% hydrogen, 3% nitrogen, and smaller amounts of calcium, phosphorus, potassium, sulfur, and many other elements. By number of atoms rather than mass, hydrogen dominates overwhelmingly. Because hydrogen atoms are so light, even though they make up only 10% of your mass, they make up about 60% of your atoms by count. About 4.2 times 10 to the power of 27 of the atoms in your body are hydrogen atoms. That's over 4 billion hydrogen atoms, each consisting of a single proton and a single electron. Each proton smaller than a femtometer across. Each atom mostly empty space. Every single atom in your body was forged somewhere specific. The hydrogen was created in the first minutes after the Big Bang, 13.8 billion years ago. The hydrogen in your body is among the oldest matter in the universe. It has existed since nearly the beginning of everything. The carbon, oxygen, nitrogen, and most other heavy elements in your body were created inside stars. Massive stars that burned through their nuclear fuel over millions of years fused lighter elements into heavier ones, then ended their lives in supernova explosions that scattered those elements into the surrounding interstellar medium. That scattered material became part of the cloud of gas and dust that collapsed to form the Sun and the Solar System about 4.6 billion years ago. The elements coalesced into planets. Eventually, on this planet, chemistry organized those elements into self-replicating molecules, into cells, into organisms, into you. The calcium in your bones was processed by at least one stellar explosion. The iron in your blood was forged in stellar cores. The oxygen you breathe came from the nuclear fusion that powered ancient stars and was scattered when those stars came apart. You are the universe looking at itself, made of material that has been through fire, vacuum, and billions of years of cosmic history. And the fundamental unit of all of that material is the atom. Small enough that 4 million of them can fit across the width of a guitar string. Small enough that the light we use to see by can't resolve a single one. Small enough that the entire concept of smallness needs to be rethought. Let's take a step even deeper into the quantum world. Beyond the quarks inside the proton, there is still more structure to consider. Or rather, there is still more to say about the structure we've already described. Quarks and gluons don't exist as a static arrangement inside a proton. The quantum vacuum inside the proton is seething. Gluons constantly split into quark-antiquark pairs that almost immediately annihilate back into gluons. These are called C-quarks. They flash in and out of existence within the proton's boundary, appearing for timescales too brief to measure directly, contributing to the proton's internal structure. The proton, at any given instant, contains not 3 quarks, but a complex, dynamic sea of gluons and quark-antiquark pairs. The 3 quarks we usually talk about, called valence quarks, are the net quarks, the stable surplus over the sea. 2 up, 1 down. But surrounding them is a quantum foam of virtual particles appearing and disappearing faster than any measurement can capture. The inside of a proton is not a simple place. It's one of the most complex, least understood volumes in physics, despite being smaller than a femtometer. The internal structure of the proton is still an active research area. The precise contribution of C quarks to the proton's spin, for example, is not fully understood. Protons have intrinsic angular momentum, called spin. Naively, you might expect the spin of the proton to come from the spins of its 3 quarks. But measurements show that the quark spins account for only about 30% of the proton's total spin. The rest comes from gluons and from the orbital motion of quarks inside the proton. Exactly how the proton's spin is distributed among these contributions is an open question in physics, known as the proton spin puzzle. It's been investigated since the 1980s. There are facilities around the world, like RHIC at Brookhaven National Laboratory in New York, dedicated in part to understanding it. Even the thing we think of as the simplest constituent of ordinary matter, the proton, contains questions we haven't answered. Now let's think about what happens when atoms are forced into extreme conditions, when the emptiness we've been describing is reduced. At normal conditions, atoms are separated by distances much larger than their own size. In a gas at room temperature and atmospheric pressure, atoms or molecules are typically tens of nanometers apart on average, far more than the atom's own diameter. In a liquid, they're closer together, roughly, at contact. They're electron clouds, touching, repelling, constantly rearranging. In a solid, they're locked into a structure, vibrating in place but not translating, still separated by their electron clouds, still mostly empty space. As you apply pressure to a solid, you're forcing atoms closer together, compressing the electron clouds. The resistance you feel is electromagnetic repulsion between those electron clouds. The electrons don't want to share space. The force required to compress matter grows rapidly as you push atoms closer. To compress matter to nuclear densities, to force the nuclei themselves together, requires pressures that don't exist anywhere on Earth's surface. But they exist in stellar cores. In the final moments of a massive star's life, when the iron core can no longer support fusion, gravity overwhelms the electron pressure. The core collapses in about 1 second. Electrons are forced into protons, combining into neutrons through the weak nuclear force. The protons and electrons essentially merge, and the result is a sphere of neutrons compressed to roughly nuclear density, a neutron star. A neutron star between about 10 and about 25 kilometers across contains somewhere between 1 and 2 times the mass of the Sun. The density is about 2 times 10 to the power of 17 kilograms per cubic meter. A cubic centimeter of neutron star material would weigh roughly 400 million tons. That's what you get when you collapse the empty space out of atoms. When you squeeze matter until the empty space is gone, the neutron star is still not as dense as a black hole. If the collapsing core is massive enough, not even the neutron pressure can stop the collapse. Gravity wins completely. The matter continues collapsing. The density approaches infinity at a mathematical point called the singularity, and our equations break down. The point at which the empty space inside atoms reaches its end, the point at which matter can be compressed no further, the event horizon of a black hole, marks the edge of what our physics can describe. The standard model of particle physics is the theory that describes the fundamental particles and forces, with the exception of gravity. It includes quarks, leptons, which includes electrons and neutrinos, and the force-carrying bosons, which includes photons, gluons, the W and Z bosons that carry the weak force, and the Higgs boson. The standard model was largely complete by the 1970s and confirmed experimentally through the following decades. The last predicted particle, the Higgs boson, was discovered at the Large Hadron Collider at CERN in 2012. About 50 years after its existence was proposed by Peter Higgs and several other physicists. The Standard Model is extraordinarily successful. It makes predictions that have been confirmed to extraordinary precision, but it is not complete. It doesn't include gravity. It doesn't explain dark matter, the invisible material that makes up about 27% of the universe's total energy content. It doesn't explain the asymmetry between matter and antimatter. If the Big Bang created equal amounts of both, they should have annihilated each other completely. But we exist in a universe made of matter. Something tipped the balance. The Standard Model doesn't explain what. It has about 19 free parameters, numbers like the masses of the quarks and the strength of the forces that have to be measured experimentally rather than derived from theory. A truly fundamental theory should derive all of these from first principles. No such theory exists yet. Physicists are working toward extensions of the Standard Model, supersymmetry, which proposes a new symmetry between bosons and fermions. String theory, which proposes that particles are actually tiny, vibrating one-dimensional strings in a higher dimensional space. Loop, quantum gravity, which attempts to quantize space-time itself. None of these has been experimentally confirmed. The Standard Model, despite being our most complete description of the atom's constituents, is widely understood to be incomplete. A framework that works extraordinarily well within its domain, but points toward physics we haven't discovered yet. The atom, for all that we know about it, still sits at the threshold of things we don't. Let's come back to everyday scale one final time. You're breathing air right now. Each breath contains roughly 10 to the power of 22 molecules. 10 sextillion. Each molecule contains atoms. Each atom contains a nucleus. Each nucleus contains protons and neutrons. Each proton and neutron contains quarks and gluons. This isn't a chain of speculation. Every level of this structure has been directly confirmed by experiment. The Bohr radius was derived from the hydrogen spectral lines. The nuclear radius was measured by Rutherford's scattering experiments and refined by many subsequent methods. The quark structure was revealed by deep inelastic scattering at laboratories, including SLAC in California, in the late 1960s. The gluon was discovered at the DESI laboratory in Hamburg in 1979, when electron-positron collisions produced 3 jet events explained by quark-antiquark gluon final states. The Higgs boson was found at CERN's Large Hadron Collider in 2012. Every piece of this picture has been tested. Every number has been measured. The atom is not a theory. It's a confirmed structure. And it is astonishingly small. And astonishingly, mostly empty. And built from things that are stranger than anything else we've encountered. Here is what I want you to take from this. The picture of the atom that lives in most people's imaginations is decades out of date. The little solar system, the hard nucleus with electrons orbiting like planets, that picture was wrong when Rutherford drew it, wrong when Bohr refined it, and it has been known to be wrong in important ways since the 1920s. The actual picture is this. The atom is a region of space in which quantum fields interact in specific ways. The electron is a quantum of the electron field. The proton is a bound state of quarks, which are quanta of quark fields, held together by gluons, which are quanta of the gluon field. The electron occupies a probability distribution, not an orbit. The proton is a dynamic sea of quarks and gluons, not a static sphere. The atom is almost entirely empty, not by accident, but because quantum mechanics prevents the electron from collapsing into the nucleus. The mass of the atom is almost entirely the energy of the strong force binding quarks together, not the mass of the quarks themselves. The atom is stable because of quantum mechanical rules that have no classical analog. Rules that say position and momentum cannot both be precisely defined. Rules that restrict the electron to discrete energy states. Rules that prevent matter from collapsing under its own electromagnetic attraction. Without those rules, none of this would exist. The atom is what physics produced after the Big Bang, after stars processed hydrogen into heavier elements, after those elements scattered through space, after gravity gathered them into new solar systems, after billions of years of cosmic evolution. This almost empty, quantum mechanical, mostly energy structure. This is the foundation of everything. What I find genuinely remarkable, and not just as a statement about physics, is this. The world feels solid. When you knock on wood, you feel resistance. When you pick up a stone, you feel weight. When you sit in a chair, it holds you. This all feels like solid stuff, meeting solid stuff. And none of it is. Every sensation of solidity is electromagnetic repulsion between electron clouds. Every sensation of weight is gravity acting on the mass of protons and neutrons, which is mostly energy from gluon fields. The physicality of the world, its resistance and substance and weight, is an emergent property, something that arises from quantum fields and quantum mechanics and produces a macroscopic world that feels nothing like its quantum underpinnings. How exactly the classical world emerges from the quantum world is a deep, partially unresolved question. It's called the measurement problem, or the problem of decoherence and the classical limit. Many brilliant physicists have worked on it. There is still no complete consensus. But the gap between what the atom is and what the world feels like is one of the deepest puzzles in physics. And standing at that gap, knowing it's there, knowing that the solidity of the ground beneath you is built from empty probability clouds and quantum fields, is one of the stranger experiences that science makes available. The next time you pick up a grain of salt, think about what you're holding. A crystalline lattice of sodium and chloride atoms, each one a cathedral of empty space with a marble-sized nucleus at the center. Each nucleus made of quarks that will never be separated, surrounded by electron probability clouds that have no definite position. The whole structure held together by electromagnetic repulsion and the quantum mechanical prohibition against electrons collapsing into nuclei. That grain of salt contains roughly 10 to the power of 18 atoms. 1 quintillion. You can barely see it. You wouldn't notice it if it fell from your hand. And inside it, there is more structure, more complexity, more strangeness, more fundamental physics than you can hold in your mind at once. That's the actual scale of a single atom. It's not just small. It's small in a way that puts it in a different category of reality from anything your senses can directly access. A world where the usual rules don't apply, where particles don't have definite positions, where mass is energy and force fields, where the empty space inside atoms is held empty by quantum mechanics itself. We built our entire civilization, every structure and machine and chemical process, from atoms we couldn't see and didn't understand. Only in the last century did we learn what they actually are. And what we learned is stranger than anything we could have guessed. The atomic mass unit is a specific number that deserves attention. When chemists and physicists talk about atomic masses, they use a standardized unit called the Unified Atomic Mass Unit, often written as U, or the Dalton, named after John Dalton. One atomic mass unit is defined as exactly 1/12 of the mass of a carbon, 1,2 atom. This works out to roughly 1.66 times 10 to the power of -27 kilograms. A hydrogen atom has a mass of about 1.008 atomic mass units. Oxygen is about 15.99. Carbon is about 12.01. These numbers look almost like whole numbers, which makes sense. The mass of an atom is dominated by its nucleus, and the nuclear mass is roughly equal to the number of protons plus neutrons times the mass of one proton. The proton and neutron have almost the same mass. So, carbon, 1, 2, with 6 protons and 6 neutrons, has an atomic mass very close to 12. The small deviations from whole numbers come from 2 sources. First, the mass of the electrons, which is tiny but non-zero. Second, and more interesting, binding energy. When protons and neutrons bind together into a nucleus, the system has less energy than the sum of the individual particles. The energy released during formation, the binding energy, corresponds to a loss of mass by E equals mc squared. The nucleus is less massive than the free protons and neutrons it's made from. This mass defect is small, but measurable. For helium, 4, 2 protons and 2 neutrons, the mass defect is about 0.03 atomic mass units. That corresponds to about 28 million electron volts of binding energy, the energy that holds the helium nucleus together, and the energy that would be released if you could somehow split the helium nucleus apart. The binding energy per nucleon, meaning the binding energy divided by the total number of protons and neutrons, peaks around iron, 5, 6. Iron, 5, 6, has the highest binding energy per nucleon of any nucleus. This means iron is the most stable element. You can release energy by fusing lighter elements into heavier ones, all the way up to iron. Beyond iron, fusing elements requires energy rather than releasing it. And you can release energy by splitting elements heavier than iron, fission, because the resulting lighter nuclei are more tightly bound. The entire landscape of nuclear energy, both fusion power and fission power, is determined by this binding energy curve. By the way, the mass defect varies across the periodic table by the fact that iron sits at the bottom of a valley in nuclear stability, and everything on either side can release energy by moving toward it. Stars do this automatically. They fuse lighter elements toward iron throughout their lives. When they die, if massive enough, they split the iron in their cores into free protons and neutrons during the collapse. And the energy released in that split, the reversal of all the binding energy accumulated over the star's lifetime, powers the supernova. In a fraction of a second, more energy is released than the star emitted during its entire lifetime of normal fusion. The mass defect of atomic nuclei is not an obscure technical detail. It's the energy source of stars. It's the origin of the elements. It's the origin of the heat that drives geology and maintains Earth's internal temperature. It's the origin of the radiation that makes cancer treatment possible. It's the energy source of nuclear power plants. And it all comes from the tiny difference in mass between a nucleus and the free particles that make it up. A difference measurable in hundredths of an atomic mass unit. In structures, a femtometer across. The periodic table is one of the great organizational achievements in the history of science. But what it actually organizes is a set of patterns in atomic structure. Mendeleev organized elements by atomic mass in 1869 and noticed that properties repeated in a pattern. Elements with similar chemical behavior appeared at regular intervals when sorted by mass. He called this the periodic law. And he left gaps in his table for elements he predicted hadn't been discovered yet. Within 15 years, several of those predicted elements were found, with properties matching Mendeleev's predictions closely. Gallium, germanium, scandium. The periodic table worked. But it wasn't until the quantum mechanical description of the atom that the reason it worked became clear. The periodicity of chemical properties reflects the filling of electron shells. Electrons in atoms occupy quantum states that are organized by energy. The lowest energy state can hold 2 electrons. The next shell can hold 8. Then 8 again. Then 18. Then 18 more. When a shell is full, the element is chemically inert. Helium, neon, argon, krypton, xenon, radon. The noble gases. They don't react with anything because their outermost electron shells are complete. There are no partially filled orbitals available to form bonds. When a shell has 1 extra electron beyond a filled shell, the element is reactive metal-like. Lithium, sodium, potassium, easy to ionize, eager to give up that extra electron. When a shell is 1 electron short of full, the element strongly attracts electrons. Fluorine, chlorine, bromine, the halogens. The chemical personality of every element is determined by how many electrons it has in its outermost, partially filled shell. And that number is determined by the quantum mechanical rules governing how electrons fill energy levels in atoms. Pauli's exclusion principle. The organization of electrons into shells by angular momentum and quantum numbers. The Aufbau principle. The rule that electrons fill lowest available energy states first. All of quantum mechanics, encoded in a 2-dimensional table that hangs on the wall of every chemistry classroom in the world. Mendeleev didn't know why the periodic table worked. He knew that it did. The why came 50 years later with quantum mechanics. The table organizes the quantum structures of atoms. And knowing those structures tells you how every element behaves, how it bonds, what compounds it forms, how reactive it is, what temperature it melts at, how it conducts electricity. Everything chemically relevant about every element flows from its electronic structure, from the way electrons fill quantum states around a nucleus, from physics happening inside a space 1/10 of a nanometer across. There is a scale of structure we haven't discussed yet, somewhere between the atom and everyday objects. The molecular scale. When atoms bond together, they form molecules. And molecules range from the simple to the extraordinarily complex. Water is 2 hydrogen atoms bonded to 1 oxygen. 3 atoms. Carbon dioxide is 1 carbon and 2 oxygens. 3 atoms. Simple. Familiar. But then there's the DNA molecule. A single strand of human DNA is about 2 nanometers wide. In the nucleus of a human cell, there are 23 pairs of chromosomes. If you stretched out all the DNA from a single human cell, end to end, it would extend to about 2 meters. 2 meters of DNA wound into a nucleus roughly 6 micrometers across. That requires extraordinary packing. The DNA is wrapped around proteins called histones, coiled and supercoiled, organized into structures called nucleosomes and chromatin. The entire DNA in a single human cell contains about 3 billion base pairs. Each base pair consists of 2 nucleotide molecules, hydrogen bonded to each other across the double helix. And the entire genome, the entire 3 billion base pairs, directs the construction and operation of a human body from a single cell. A molecule made of atoms. Each atom almost entirely empty space. The information stored in DNA, the instructions for building a human being, is encoded in the arrangement of atoms along a double helix 2 nanometers wide, 20 atoms wide. The most sophisticated information storage system ever discovered fits instructions for building a person into a space you'd need 100,000 of to equal the width of a human hair. And the mechanism that reads that information, that copies DNA and transcribes it into proteins, involves molecular machines made of 100 to 1,000 atoms, moving with precisely the right geometry to process a molecule that is itself organized at atomic scale. Biology is atomic machinery, enormously complex, but ultimately built from atoms bonded together, interacting electromagnetically, following quantum mechanical rules. Consider what it means that you can understand this. The fact that you can. The capacity to comprehend the scale of an atom, to reason about quantum mechanics, to follow an argument about nuclear binding energies and electron wave functions, is itself a property of atoms organized in a particular way. The neurons in your brain are cells. Cells made of molecules. Molecules made of atoms. The electrical signals traveling through your neurons are ion flows across membranes, sodium and potassium ions. Atoms carrying electric charge, moving through protein channels. Proteins made of amino acids. Amino acids made of carbon, hydrogen, oxygen, nitrogen, sometimes sulfur. Atoms arranged in specific 3-dimensional structures. The thought you're having right now, whatever it is a pattern of electrochemical signals moving through a network of about 86 billion neurons, each connected to roughly 7,000 others. The pattern of those signals is the thought, and the signals are ion currents, and the ions are atoms. It goes all the way down. There is no level at which atoms become something else. The atom you've been reading about, the almost empty quantum mechanical structure with a nucleus smaller than a femtometer and an electron probability cloud extending 100 picometers outward, that thing, in enormous numbers, organized in specific patterns, is what consciousness is made of. Whether consciousness is something more than the pattern, whether subjective experience is reducible to atomic physics, is a question philosophy hasn't answered. But the atoms are there. Every thought is built from them. Every memory. Every sensation. Every moment of recognition. The matter doing the thinking is the same matter we've been describing all along. And yet something strange is true. None of the atoms in your body has a privileged relationship to you. Your body replaces most of its atoms over years. The oxygen in the air you breathe enters your bloodstream and becomes part of your cells. Eventually, it leaves as carbon dioxide. The hydrogen in the water you drink becomes part of your tissues. Eventually, it leaves. The carbon in the food you eat becomes part of your proteins. Eventually, it leaves. The atoms cycling through you right now were somewhere else before. Part of water, part of soil, part of plants, part of other organisms. And they'll be somewhere else again after. There is no specific atom that is essential to you. No atom that has always been yours and always will be. The pattern remains. The atoms change. You are not the atoms. You are what the atoms are doing. And what the atoms are doing is something quantum mechanics can describe in principle. Quantum mechanics describes the behavior of individual atoms and particles with extraordinary precision. It tells you the energy levels, the bonding, the reaction rates. But the pattern that emerges from trillions of atoms working together, the pattern that is a living organism, a person, a conscious experience, that pattern is something that quantum mechanics doesn't directly address. Not because it violates quantum mechanics. It doesn't. But because the pattern is at a level of description so far removed from the quantum mechanical one that the language doesn't translate. This is the hard part of atomic physics. The atoms are understood. The patterns they make are not. Not fully. Not yet. Let's come back to the numbers one final time. To fix the scale in your mind before we're done. A hydrogen nucleus, a proton, has a radius of about 0.85 femtometers. A femtometer is 10 to the power of negative 15 meters. A hydrogen atom has a radius of about 53 picometers. A picometer is 10 to the power of negative 12 meters. The ratio of atom to nucleus is about 60,000 in radius. About 240 trillion in volume. A human red blood cell is about 8 micrometers across. That's 8,000 nanometers. Or 8 million picometers. One red blood cell is about 150,000 times wider than a hydrogen atom. A red blood cell contains about 270 million hemoglobin molecules. Each hemoglobin molecule contains about 10,000 atoms. The visible world around you, the chair, the floor, the walls, all of it built from structures invisible to the naked eye, which are themselves built from structures invisible to the most powerful optical microscope, which are themselves built from structures smaller than the wavelength of X-rays. The full range from proton to human being spans 13 orders of magnitude. 13 powers of 10. That means a human being is to a proton as a human being is to, roughly, 1,000th of the thickness of the observable universe. The same ratio. In the other direction. We sit in the middle of the scale of things. Larger than atoms by many orders of magnitude. Smaller than the cosmos by many more, and made entirely of the thing we've been trying to understand all evening. The atom, almost entirely empty, held apart by electromagnetic repulsion, held together by the strong nuclear force, governed by quantum mechanics, made mostly of energy, built from fields that fill all of space. And somehow, despite all of that, making the world feel exactly as solid and real and definite as it does. That is the atom. That is what everything is made of. And we built modern civilization before we even knew it existed. Now we know. And what we know is stranger than anything we could have guessed. One set of experiments shows something about the atom that no amount of theoretical description quite prepares you for. They showed that the atom, for all its emptiness, for all its quantum strangeness, is real, tangible, manipulable. In 1989, Don Eigler and Erhard Schweizer at IBM's Almaden Research Center in California arranged 35 xenon atoms on a nickel surface. They used a scanning tunneling microscope tip, dragging each atom individually to a precise position. The atoms spelled out 3 letters: I, B, M. The letters were about 5 nanometers tall. To see the image clearly, you had to use the same scanning tunneling microscope that placed the atoms. The image had to be published at high magnification. But the letters were there, made of atoms, arranged by a machine guided by human intention. Eigler later reflected that when he first saw atoms in his microscope, he realized these weren't just intellectual constructs anymore. They were things. Things you could move. Things you could arrange. The atom went from a theoretical entity inferred from chemical ratios and spectral lines to something you could pick up and set down. In the years since, this kind of work has progressed substantially. Atoms and molecules have been used to construct rudimentary switches and logic gates. Quantum information has been stored in single atoms. The electric current through a single atom has been measured. Chemical bonds between individual molecules have been directly observed. Individual molecules have been weighed. Single atoms have been identified by species and positions simultaneously. The technology built on this understanding, from transistors small enough that a chip contains billions of them in the area of a fingernail, to quantum computers that manipulate quantum states of individual atoms or ions, represents the translation of atomic physics into practical capability. We are not just observers of the atomic world. We have become, to a limited but real degree, engineers of it. And the scale at which we work, the scale at which we set individual atoms like tiles in a mosaic, is the scale we've been trying to describe all along. Less than a nanometer. Below the threshold of anything visible. In a world that requires entirely different instruments to perceive. There is one more thing to say about scale. And it's the most personal version of everything we've discussed. Right now, in the neurons in your brain, there are ions moving. Sodium ions flowing into cells through protein channels. Potassium ions flowing out. These flows generate the electrical signals that constitute your thoughts, your perceptions, your memories. A sodium ion is a sodium atom that has lost 1 electron. It carries a positive charge. Its radius is slightly smaller than a neutral sodium atom, roughly 116 picometers in its ionic form. Thousands of these cross each protein channel every millisecond. The protein channel itself is made of roughly 3,000 amino acids, arranged in a specific 3-dimensional structure that is exquisitely selective. It allows sodium in, but excludes potassium. The selectivity depends on the precise geometry of the channel's interior, on the distances between specific atoms in its structure, on the way water molecules coordinate with ions of different sizes. The channel distinguishes between sodium and potassium, 2 similar metal ions, because the atomic geometry is precise enough, because atoms bond at specific angles and distances determined by quantum mechanics. And because that precision, that atomic scale geometry, the channel can filter correctly. If the geometry were slightly off, if the atoms were arranged differently, the channel would fail. the neuron would fail. The signal would fail to propagate. The thought, whatever thought is happening right now as you read this, would not happen. Every thought you have ever had, every memory, every dream, every decision, all of it has depended on the correct functioning of ion channels, on the geometry of proteins built from atoms, on the charge of ions that are atoms minus one electron, on quantum mechanical rules that determine the size and shape and bonding angles of atoms. You are reading about the atom, and the reading is being done by atoms. The understanding is atomic. The wonder, if you feel any, is ionic currents through protein channels in neurons built from molecules, built from atoms that are almost entirely empty space. That chain from atom to wonder is complete. And it is one of the genuinely strange facts about the universe that the matter in it has organized itself in a way that allows this. Not everywhere, not often, but here, now. There's another dimension to atoms we haven't fully explored yet. The way they interact with each other, the way they combine, the way they communicate through light. The fact that atoms can absorb and emit light is not incidental to what atoms are. It's central. And the mechanism is beautiful in its simplicity once you understand the quantum mechanical picture. The electron in a hydrogen atom can exist in different energy states. The ground state is the lowest. The electron can be bumped to higher states by absorbing a photon whose energy exactly matches the gap between two levels. Exactly. Not approximately. Exactly. If the photon's energy is slightly too high or slightly too low, the atom won't absorb it. The photon will pass right through as if the atom weren't there. This is quantum selectivity, and it means that each type of atom has a completely unique absorption and emission spectrum, a unique set of photon energies that it will interact with and no others. The photon energy corresponds to a specific wavelength of light, which corresponds to a specific color. So when electrons in hydrogen atoms fall from higher to lower energy levels, they emit photons of specific colors. The red of one transition, the blue-green of another, the violet of a third. These aren't arbitrary. They're determined by the mathematics of quantum mechanics applied to a single proton and a single electron. The same mathematics that explains the emission spectra of every other element. And because different elements have different numbers of protons and electrons, and because those different configurations produce different energy level spacings, every element emits a completely unique pattern of light. This is not just a curiosity for laboratory spectroscopists. This is what makes astrophysics possible. When astronomers point a spectrograph at a distant star and spread its light into a spectrum, they see dark lines at specific wavelengths. These are absorption lines. Photons at those specific wavelengths have been absorbed by atoms in the star's outer atmosphere. By comparing those lines to the known spectra of elements measured in laboratories on Earth, astronomers can determine the chemical composition of a star light years away. They can measure how much hydrogen it contains, how much helium, how much iron, whether it has unusual abundances of particular elements. They can measure the temperature of the star's surface from which part of the spectrum is brightest. They can measure how fast the star is rotating from the widths of its spectral lines. They can detect magnetic fields from the splitting of spectral lines in strong fields, the Zeeman effect, discovered by Peter Zeeman in 1896. All of this from the quantum mechanics of electrons jumping between energy levels inside atoms. The information encoded in the spectrum of a star is extraordinarily rich, and all of it originates in the same process. An electron absorbing or emitting a photon as it moves between quantum energy levels inside an atom, inside something smaller than a billionth of a meter. There's another kind of emission from atoms that deserves attention. Radioactivity. Not all atoms are stable. Some nuclei have configurations of protons and neutrons that are energetically unstable. They want to reach a lower energy state, and they do this by emitting particles or radiation. Alpha decay is one mechanism. The nucleus ejects a tightly bound cluster of 2 protons and 2 neutrons, which is the helium-4 nucleus. This happens because the helium-4 cluster is particularly stable and because the remaining nucleus, 4 mass units lighter and 2 protons fewer, may be in a more stable configuration. Alpha decay releases substantial energy. The alpha particle is emitted at high speed, but alpha particles can be stopped by a few centimeters of air or a thin sheet of paper. They're energetic, but not penetrating. Beta decay is different. In beta minus decay, a neutron inside the nucleus converts to a proton by emitting an electron and an antineutrino. This is mediated by the weak nuclear force. The weak force is the second short-range nuclear force, distinct from the strong force. It can change the flavor of quarks. A down quark in the neutron converts to an up quark, changing the neutron into a proton. The emitted electron travels at close to the speed of light and can penetrate several millimeters of aluminum. Beta plus decay is the reverse. A proton converts to a neutron by emitting a positron and a neutrino. Gamma radiation is different again. It's not a particle emission. It's photon emission. When a nucleus is in an excited energy state and drops to a lower one, it emits a high-energy photon, a gamma ray. Gamma rays are electromagnetic radiation of extremely short wavelength, far shorter than X-rays. They can penetrate centimeters of lead. Radioactive decay is the nucleus finding a lower energy configuration. It's the same basic principle as an electron emitting a photon when it falls to a lower energy state, but happening in the nucleus instead of the electron cloud, and often releasing far more energy. The energy difference between nuclear energy levels is far larger than the energy difference between electron energy levels, which is why nuclear reactions release millions of times more energy per atom than chemical reactions, and why nuclear weapons and reactors are so staggeringly more energetic than conventional explosives and chemical fuel. Let's think about what happens when you compress matter beyond atomic scale. We mentioned neutron stars earlier, but there's more to say about what happens on the way there. In a white dwarf, the endpoint of stars like the Sun, matter is compressed to roughly 1,000,000 times the density of water, about 1 ton per cubic centimeter. This is dense enough that the electrons, which normally occupy the vast empty space of atoms, are squeezed into close contact with each other. They can't get any closer because of a quantum mechanical principle called the Pauli exclusion principle. The Pauli exclusion principle, discovered by Wolfgang Pauli in 1925, states that no 2 electrons in the same quantum system can occupy the same quantum state simultaneously. 2 electrons can share the same region of space only if their spins point in opposite directions, giving them different quantum states. Once all the available states are filled, electrons resist further compression. This resistance is called electron degeneracy, pressure. And it's not electromagnetic repulsion. It's a quantum mechanical effect with no classical analog. It's the result of the mathematical properties of fermions, which is the category of particles that includes electrons and quarks. Particles with half-integer spin, which includes all matter particles, obey what's called Fermi-Dirac statistics. And one consequence of those statistics is that fermions resist being pushed into the same quantum state. They resist occupying the same space. White dwarfs are held up by electron degeneracy, pressure, not by the ordinary electromagnetic repulsion between electron clouds that holds up a rock or a table, by the quantum statistical property of electrons that prevents two of them from being in the same quantum state. A white dwarf, the size of Earth, can contain roughly the mass of the Sun. A teaspoon of white dwarf material would weigh about 5 tons. If the mass exceeds about 1.4 solar masses, the Chandrasekhar limit, electron degeneracy, pressure, is not enough. The electrons are forced into the protons. Neutron degeneracy, pressure from the resulting neutrons takes over. The star becomes a neutron star. And if the neutron star is massive enough, even that fails, and nothing stops the collapse. Every step of this progression, from atoms to white dwarfs, to neutron stars to black holes, is the story of what happens when the empty space of atoms is progressively eliminated, when quantum mechanics loses its battle against gravity. Now, let's think about the early universe, because the atoms we've been discussing didn't always exist. In the first moments after the Big Bang, the universe was too hot and too dense for atoms to form. At the temperatures that existed in the first seconds, roughly 10 to the power of 10 Kelvin and higher, any proton and electron that came close enough to bind would immediately be torn apart by a photon with enough energy. The universe was a plasma, a soup of free quarks and gluons for the first millionths of a second, then a soup of free protons, neutrons, electrons, and photons, once the temperature dropped enough for protons and neutrons to form. In the first few minutes, when the temperature dropped to roughly 1 billion Kelvin, nuclear fusion became possible. Protons and neutrons began combining to form deuterium, helium-3, helium-4, and tiny amounts of lithium. This is Big Bang nucleosynthesis. Within about 20 minutes, the universe had cooled enough that this nucleosynthesis stopped. The composition was locked in. Roughly 75% hydrogen and 25% helium by mass, with trace amounts of heavier elements. This is the composition we observe today in the oldest, most pristine regions of the universe, and it matches the predictions of Big Bang nucleosynthesis to remarkable precision. But atoms still didn't exist. Protons and electrons were free, not bound together. The photons in the universe were constantly scattering off the free electrons, making the universe opaque, like trying to see through a dense fog. Light couldn't travel freely. Then, about 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin. At that temperature, protons and electrons could finally remain bound together. Hydrogen atoms formed, and when they did, the photons that had been trapped by the constant scattering off free electrons were suddenly free to travel. The universe became transparent for the first time. Those photons are still traveling today. We can detect them as the cosmic microwave background radiation, the afterglow of that moment when atoms formed. The atoms that formed at that moment were almost entirely hydrogen, with some helium from Big Bang nucleosynthesis. The heavier elements came later, built in stellar interiors, scattered by supernovae, incorporated into new solar systems. The atoms in your body took billions of years to assemble, and the moment they began to be possible at all, the moment the universe first had atoms, produced a glow we can still detect today as a faint microwave signal coming equally from all directions in the sky. There's one more thread we haven't pulled yet: the neutrino. It passes through atoms constantly, billions per second, through every square centimeter of your body. And it barely interacts with atoms at all. Not because it's tiny, though it may be nearly or exactly a point particle, but because it interacts only through the weak nuclear force, which is extraordinarily feeble compared to electromagnetism. The neutrino was proposed by Wolfgang Pauli in 1930 to solve a problem with beta decay. Energy appeared to be disappearing in beta decay measurements. A neutron decaying to a proton should produce an electron, and, according to energy conservation, the electron should carry all the released energy. But measured electrons came out with a range of energies, less than the total released. Where was the missing energy going? Pauli proposed, reluctantly, that the missing energy was carried by an invisible particle he called the neutron at first, until Chadwick's discovery of the actual neutron required a new name. Enrico Fermi named it the neutrino, meaning little neutral one. Pauli was initially embarrassed by the proposal. He thought it was too speculative. He said he had done something terrible by predicting a particle that could probably never be detected. He was wrong. The neutrino was detected in 1956 by Clyde Cowan and Frederick Rines, using a nuclear reactor as a neutrino source. The reaction they looked for was the inverse of beta decay, an antineutrino interacting with a proton to produce a neutron and a positron. They saw it. The neutrino was real. Rines received the Nobel Prize in Physics in 1995 for the discovery. Cowan had passed away by then. Nobel Prizes are not awarded posthumously. Neutrinos come in 3 varieties, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos, named after the charged leptons they're associated with. And neutrinos have a strange property. They oscillate between flavors as they travel. An electron neutrino produced in the sun's core can arrive at Earth as a muon neutrino or a tau neutrino. This is called neutrino oscillation, and it was confirmed experimentally in 1998 by the Super Kamiokande detector in Japan, and in 2001 by the Sudbury Neutrino Observatory in Canada. Neutrino oscillation proves that neutrinos have mass. Because massless particles travel at the speed of light and experience no time, without the passage of time, there can be no oscillation. Oscillation requires a particle to have mass. The exact masses of the neutrino flavors are still being measured. They are extraordinarily small. Less than about 0.1 electron volts divided by c² for the heaviest flavor. More than 1 billion times lighter than the electron. But they're not zero. Neutrinos have mass. And the Standard Model, in its original form, predicted they didn't. Neutrino mass is currently one of the clearest indicators that the Standard Model is incomplete. There's physics beyond it. Physics we haven't fully described. And it was revealed by a particle that passes through the entire Earth as easily as you might walk through a doorway. A particle that barely notices atoms exist. Let's think about measurement. Because measuring things at the atomic scale is not just technically challenging. It raises questions about what measurement itself means. When we say we've measured the radius of the proton, what did we actually do? We scattered electrons off protons at various angles and energies. We analyzed the pattern of scattering. We fit that pattern to a model. The model includes a parameter for the proton's radius. We extracted the best fit value of that parameter. That's the measurement. It's an inference. We didn't put a ruler against the proton. There is no ruler that small. We inferred the size from how things scatter off it. And the answer depends on the model we use, the energies of the particles we scatter, the precision of our detectors, and the theoretical framework we're working in. Different experiments have given slightly different values for the proton radius. The electron scattering experiments historically gave a value of about 0.87 femtometers. But a more precise experiment using muonic hydrogen, where the electron is replaced by a muon, gave a value of about 0.84 femtometers. The discrepancy was only about 4%, but it was statistically significant. This became known as the proton radius puzzle, and it occupied physicists for about a decade. The prevailing resolution is that the muonic hydrogen measurement was more accurate, and the proton radius is closer to 0.84 to 0.85 femtometers. But the puzzle illustrated something important. Even for the best understood particle in physics, even for the proton that sits at the center of every hydrogen atom, there are measurements we're still refining. Structures we're still characterizing. Numbers we're still pinning down. The atom is known. But known to what precision is always the follow-up question. And precision matters enormously in physics. The history of atomic physics is, in large part, a history of increasingly precise measurements, revealing new layers of structure or new discrepancies between theory and experiment. Each discrepancy eventually leading to new theory, or new particles, or new physics. The proton radius puzzle is a small, recent example. Larger examples include the anomalous magnetic moment of the muon, where current measurements deviate slightly from standard model predictions. This deviation, if confirmed at higher precision, would indicate physics beyond the standard model. Precision measurement, at the atomic scale, is one of our sharpest tools for finding the edges of what we know. The atom isn't just a subject of pure scientific curiosity. Understanding the atom transformed the practical world. The semiconductor at the heart of every computer, every phone, every digital device depends on the quantum mechanical behavior of electrons in crystalline solids. Transistors work because electrons in semiconductor materials can be controlled by electric fields in ways that depend directly on quantum mechanics. The band structure of semiconductors, which determines which energies electrons can and cannot have, is a quantum mechanical property of the crystalline lattice. Without quantum mechanics, without understanding the electron's behavior in materials at atomic scale, there would be no transistors, no computers, no internet, no modern telecommunications. Every digital technology that exists is built on atomic physics. Lasers are another example. A laser works by stimulating atoms or molecules to emit light coherently, all in phase with each other. This requires understanding exactly how electrons move between energy levels in atoms. How stimulated emission works. The process Einstein described in 1917, where a photon can trigger an excited atom to emit another photon of exactly the same energy, phase, and direction. The entire field of photonics, which is transforming telecommunications and computing, rests on this. Magnetic resonance imaging, MRI, used in hospitals worldwide, works by manipulating the quantum mechanical spin of hydrogen nuclei in your body. The proton has spin. It behaves like a tiny magnet. In a strong external magnetic field, proton spins precess at a characteristic frequency called the Lama frequency. Radio frequency pulses at that frequency can flip the proton spins. When the spins relax back to their equilibrium orientation, they emit radio frequency signals that can be detected. The signals from different tissues differ because the protons in different molecular environments relax at different rates. That difference is what produces the contrast in an MRI image. Every MRI scan is a direct measurement of proton spin behavior in atomic nuclei inside the patient's body. Atomic clocks, which are the most precise timekeepers ever built, work by measuring the frequency of radiation emitted during transitions between specific energy states of cesium-133 atoms. The second, the fundamental unit of time in the International System of Units, is defined as exactly 9,192,631,770 oscillations of the electromagnetic radiation corresponding to the transition between two hyperfine energy levels of the cesium-133 atom. The definition of the second is atomic. The precision of GPS, which most people think of as a mapping tool, requires atomic clock accuracy. A GPS position calculation requires timing signals from multiple satellites to a precision of nanoseconds. A nanosecond error corresponds to a position error of about 30 centimeters. Without atomic clock accuracy, GPS position errors would be kilometers. Navigation, surveying, financial transactions, internet synchronization, all of it depends on our understanding of atomic energy levels. The atom is not just a scientific curiosity. It is the foundation of the modern world. And yet most of what we've described, the electron clouds, the quantum energy levels, the nuclear structure, the quark content of protons, all of this is invisible. None of it can be directly seen. None of it can be directly felt. The direct human experience of atoms is entirely mediated by their collective effects. The hardness of a surface, the taste of salt, the warmth of sunlight, the color of a flower. All of these are macroscopic emergent properties of a world built from quantum fields and probability distributions. The gap between what we experience and what is actually there is one of the deepest divisions in physics. On one side, the quantum world of atoms and electrons and probability clouds and quantized energy levels. On the other, the classical world of definite positions and predictable trajectories and solid objects. There is a process by which the quantum world transitions into the classical world. Physicists call it decoherence. When a quantum system interacts with its environment, the quantum superpositions, the ability of particles to be in multiple states at once, are rapidly destroyed. The interaction with the environment entangles the quantum system with a vast number of environmental degrees of freedom. The quantum information becomes distributed across so many particles that it becomes effectively inaccessible. The quantum superposition is still technically there in the full quantum state of everything. But for all practical purposes, it's gone. The system behaves classically. This is decoherence. It happens extraordinarily rapidly for macroscopic objects at room temperature. in about 10 to the power of negative 23 seconds for an object the mass of a grain of sand, which is why we never see ordinary objects in quantum superpositions. They decohere far too quickly. But at the atomic scale, where interactions with the environment are fewer and weaker, quantum effects persist. Atoms can exist in superpositions. Electrons can tunnel through energy barriers. Wave functions can interfere. These are the quantum mechanical effects that make chemistry work and that technology now exploits in devices like quantum computers. The atom lives at the boundary between the quantum and the classical. It is large enough to have some definite properties, a well-defined mass, a definite number of protons, but small enough that its electrons remain genuinely quantum, that the electron's position is genuinely undefined, that quantum effects shape everything it does. This boundary is not sharp. It's not a wall. It's a gradient. And where exactly the boundary lies, how exactly the quantum becomes the classical, is still an open question. The measurement problem in quantum mechanics, which asks how definite classical outcomes arise from quantum probability distributions when a measurement is made, is not fully resolved. Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation says the wave function collapses when measured. The many worlds interpretation says all possible outcomes occur in branching parallel universes. Decoherence-based interpretations say that classical behavior emerges from quantum mechanics through interaction with the environment, without needing any special collapse. These interpretations make the same experimental predictions. No experiment has distinguished between them. The atom sits at the center of this unresolved question. It's the object that makes quantum mechanics necessary. And it's the object whose behavior we're still debating how to interpret. We are, each of us, made of roughly 7 times 10 to the power of 27 atoms, 7 with 27 zeros after it, mostly hydrogen by number, with oxygen, carbon, nitrogen, and a long list of other elements present in smaller amounts. Every one of those atoms has a nucleus. Every nucleus is a proton, or protons and neutrons. Every proton and neutron contains quarks. The quarks in your body have been there since the moments after the Big Bang. They have been part of hydrogen gas clouds, parts of stars, parts of planetary material, parts of ocean and atmosphere and biology, for 13.8 billion years. They will be part of something else long after you're gone. Long after the sun expands into a red giant and the Earth is gone. Long after the stars of the Milky Way have burned out. Long after the cold remnants of galaxies have evaporated or fallen into black holes, protons, if they're stable, could exist for a time that makes the current age of the universe look like an instant. Some theories predict proton decay on timescales of 10 to the power of 34 years or longer. The current age of the universe is about 14 billion years, which is about 1.4 times 10 to the power of 10 years. If protons do eventually decay, the quarks inside them will not survive as quarks. They'll transform into lighter particles. Leptons. Photons. The universe does not destroy matter. It transforms it. The atoms you're made of have been countless other things, and will be countless other things again. The fact that they are briefly organized into you, into a pattern complex enough to read about the very atoms it's made of, is one of the stranger and more remarkable facts about the universe. Not in a mystical sense, in a literal, physical sense. The atoms in your neurons are generating the experience of contemplating atoms. The same quarks and electrons that form all matter everywhere have been organized, here and now, into a structure that can look inward at itself, that can measure itself with instruments, that can deduce the size of its own protons, that can figure out that everything it is made of is mostly empty space. That's not a poetic observation. It's just an accurate description of what's happening. And the scale that makes it strange is the scale we've been talking about all along. 10 to the power of negative 15 meters for the proton. 10 to the power of negative 10 meters for the atom. 62,000 times more empty space than matter. The world made of almost nothing. And that almost nothing making everything. Good night.